So welcome back, and we are looking at chapter 23, and we're picking up at the alveoli. And what this means is, in the previous 15 minutes or so, we broke down the basic physical structures for gas conduction into the functional site where gas exchange will occur. What I mean by that, of course, is oxygen is moving in as it's passing as part of all the gases that move into the lungs, and carbon dioxide will be transferred out. Many other things are happening, but these are the two most important concepts we want to wrap our brain around. But let's start with the two types of alveolar cells that are going to allow that to happen. See if I can do this. I'm not too impressed with my skills at this point in time. Yeah, there we go. What happened? Let's go back here. Let's go wrong direction. Where did you go? There we are. Fantastic. Type 1 alveolar cell forms a continuous lining of the site where essentially gas exchange is going to occur. And gas exchange, as far as we're concerned, is going to be oxygen moving in one direction towards hemoglobin in red blood cells, and carbon dioxide moving in the opposite direction from bicarbonate, carbon dioxide, and carbaminohemoglobin moving into the space you will now exhale carbon dioxide. And there are type 2 alveolar cells. These are also called septal cells. And what they're doing, of course, is they're secreting alveolar fluid. This fluid is inside the alveoli itself, different than the pleural fluid. And what's important to remember here is that that is going to ensure that the alveolus itself, that cell-shaped outpouching, doesn't collapse on top of itself and remain collapsed. It's important that the cup has a reduced surface tension level. That's the purpose of that alveolar fluid. And in doing this, this is actually how you can make sure that you can exchange gases. What is the alveolus actually doing? Well, I just told you it's made up of type 1 and type 2 cells. It has an epithelial basement membrane. It has a capillary basement membrane. It has a capillary endothelium. It's pretty thin, but take a look at this. And back in chapter 19 and 21, we said, look, you have a capillary bed. Well, that was just a capillary bed. Here, not only do you have the epithelial basement membrane, you have a capillary basement membrane, as well as a capillary endothelium. So we have a large distance to travel for deoxygenated blood as well as oxygenated blood. Okay? And it's also going to support all of the other structures inside that space. So not only is it going to the hemoglobin inside of red blood cells, it's supporting everything else inside the actual lungs as well. Let's go back here. You can see this cartoon here. The point, if here's an alveolus and here's a septal cell that's secreting the surfactant molecules. You're going to see here's an alveolar macrophage. Remember the previous 15 minutes I said something about something trying to turn you into dinner. These guys are running around and ingesting as much of that as they can. And here's that elastic fiber. Remember I said these get stretched out as the pressure changes inside the lungs. But here is a membrane where you're actually having gas exchange occur. And here's the red blood cell. Inside the red blood cell are the hemoglobin molecules, where oxygen is now going to move out of that alveolar space into the hemoglobin. Carbon dioxide is going to move down its concentration gradient. Okay? And in the moment or two that these are in this space, that's how we're all going to move these gases around. So what we're actually talking about when we're inhaling and exhaling and the gas is actually getting into the lungs is we are talking about pulmonary ventilation, where what we're doing is simply moving gases, and that's why it's called gas exchange. Remember, the carbon dioxide moves out of the body, the oxygen moves into the body by binding to that hemoglobin. There's a lot of reasons for this. I'm just going to give you a sort of snapshot at this point in time. Carbon dioxide is not soluble in water, so hemoglobin affords that opportunity. Carbon dioxide is very soluble, but it's at a really high concentration, so it's going to move down its concentration gradient to get out of the body. Internal respiration, this is the stuff that really seems to create trouble for people. All this really means is for us to ensure that cellular respiration occurs, let's put a underline, italic, bold there. Make sure you also understand, let's get rid of that and say, where? I'm going to put this here because everybody inside the room should know that we make ATP inside of cells that are eukaryotic inside the mitochondria. So ultimately you're thinking that all that gas you're inhaling is carrying a subset of it, which is oxygen, about 20%, and it's traveling to the mitochondria so we can make ATP. And if that's blowing your mind at this point in time, okay, we can work with that. So let's inhale. Okay, we do this before your exams and all that sort of stuff, right? But really what you're doing, of course, is you are changing the pressure inside the alveoli. Okay, I don't think it has anything at all to with lust. Okay, that's a typo. I apologize for that. The pressure becomes just below lower than atmospheric pressure. So outside of your body right now, you're moving around at around 1 atmosphere, which is 760 millimeters of mercury. As you stretch all of those tissues apart, remember I said you're going to literally use the elastic, the pleural fluid, you're moving everything apart, the pressure drops inside the thoracic cavity. And what's going to happen here is the gases will now move into the space because it is below atmospheric pressure. Let's do this again. Okay. This is usually the way you say it inside chemistry class, right? Normally, as you increase pressure inside a space, okay, it's an inverse relationship. So you push that piston down, you increase the pressure inside of it. If you decrease the pressure, you drop it, and therefore more molecules can move inside the space. And that's actually what inhalation is. Because the diaphragm is innervated by C3, C4, and C5, which you know as the phrenic nerve. Let's put that in there. Phrenic. Okay. It's going to actually cause the flattening of the dome of musculature, and it's going to cause most of the gases to actually enter into the lungs during, notice what I'm calling it here, normal, quiet breathing. You're like, what's normal, quiet breathing? Well, you're sitting here right now. You're not running for your life. It takes absolutely no effort. Just inhale. Now pay attention to your exhale. No work is required. Because of the elasticity of the tissues, you now can just simply push that gas out of your lungs. However, if you're running for your life, we'll talk about that in a few minutes, what you can see is, so before we get to what happens when you're running for your life, remember those things with the big fangs chasing you across the Serengeti or whatever it is, the remaining 25% from this 75%, so you add these two values together and you obviously get 100%, is from the external intercostals. So take your fingers, find some ribs, go in between those bones, and those are your external intercostals. You can't palpate the internal intercostals. You'd have to go underneath your rib cage and push from the inside outside. So the remaining 25% for normal quiet breathing actually comes from external intercostals. You know, that's like fantastic information for like a true and false question. So what's going to happen, of course, we're going to drop the pressure inside that space, and this is what it looks like. Let's see if we can get the slide to change for you here. These muscles, okay, are going to move the articulation, the heads of each of these bones at the spinous processes down here. So the heads of each of these push into the actual bone back here that makes up your spinal column, and it flares outward. Put your hands on the outside of your rib cage. Inhale, feel which way your ribs actually move. They move outward and they move upward, and this is what increases the space inside the lungs, and therefore you will inhale. You can change this if you're running for your life, and if you've ever thought about the last time you actually ran really hard, you felt all sorts of muscles moving in your body that got tired, probably faster than they really ought to have. You'll figure out how that happens later. When we're exhaling, normally, nothing's required. The elasticity returns it back to its normal position. But we can change this around because inside your body, I should say outside your body, pay attention to this, outside your body at 760 millimeters of mercury at sea level, these lungs are designed to function. So what happens is, as you inhale, you're going to increase the size and the volume of the lungs just deep to the rib cage here. That pressure drops to about 758 millimeters. That's your inhalation. And what's going to happen is during normal quiet exhalation, the diaphragm and external intercostals relax. And that's going to force the gas out of your lungs, because now what's happened, of course, is the pressure has now increased. So you can actually push the gas out of your body. Okay? This is the case. What I need you to understand, and what you probably want to understand as well, is the surface tension inside alveolar fluid is what's going to actually account for 2/3 of the lung elastic recoil. Okay? That's the force. Sum all of those alveoli together, they push enough gas out. And because your lungs are compliant, at least in our youth, right? Lung compliance means that the lungs and the chest wall expand easily. Should there be a reason for that not to happen, let's imagine we scar all of that tissue with repeated infections inside your lungs that have caused scarring of the tissue. You would actually have a low compliance, which means the lungs and the chest wall wouldn't expand easily, which means you'd actually have a reduced amount of elasticity and surface tension, and therefore it'd be really hard to breathe. Okay? So what are the volumes we need to think about? Well, the first volume I want you to think about is this thing that's called a minute ventilation. If you're sitting there, you're actually, and you're watching somebody breathe. Don't do this unless the other person knows what you're doing. Otherwise, you look kind of weird. But, a normal person has about 12 breaths per minute. You can tell people who have some form of breathing dysfunction or heightened anxiety or something by just the simple rate with which they're breathing. A long, slow breath is what you're aiming for over the course of 60 seconds, and you're pushing about 500 mils of air in and out, and we call that tidal volume. Okay? That's important, because that 500 mils you're going to see as part of an entire chart that we need to put together. So if you're pushing 12 breaths at 500 mils per, you're pushing about 6 liters. 6 liters of a gas. And that gas is now the minute ventilation that you're actually now moving. Okay, so what does this actually look like? You're going to see this figure inside your textbook, and I think it's probably one of the worst figures you have inside your textbook because they've decided to take some really simple ideas and make them really confusing for you. This is you with lungs, the far right side of this figure, and you have a total potential capacity. For males, it's about 6,000 milliliters. For females, it's about 4,200 milliliters. And these should all have an asterisk next to them because, hey, there could have some women inside the class that are well above 6,000 milliliters, right? The interesting thing is, this is your vital capacity. It is the expiratory reserve tidal volume, which I just mentioned a moment ago, and the inspiratory reserve volume. This is what you need to keep you alive. Hence, its name, vital capacity. Your normal inspiration, meaning what you inhale and what you could potentially inhale, is that tidal volume plus the inspiratory reserve volume. So you're sitting at your desk going, oh, life is so boring. But then, I don't know, Velociraptor shows up at the door and you have to start running for your life. This is the total amount of gases you could get into your lungs before they start to fail. And here's what's interesting. Well, Mother Nature has realized she needs to get rid of that carbon dioxide, so she has an expiratory reserve volume that will allow you to push more of the inspiratory capacity out here so you can get rid of that carbon dioxide. Once you get away and you're alive and all that sort of stuff, take a look at what's actually moving. This is the 500 mils that are moving through that entire conduit system from your nose to the alveolus at about 500 mils. Okay, so really what we have is we have the inspiratory reserve volume here, tidal volume, expiratory reserve volume, and this residual. And this residual is, I'll explain it more inside class, but one way to think about this is if you ever had to get all of the gases out of the lungs, this would be what would actually come out last. Okay? Cool. So let's move to the lung volume. Okay? And like I said, only 70% of that tidal volume actually reaches the respiratory zone. And if I haven't said that, make sure you read about it inside your textbook. I know I just said it. So what's going to happen, of course, is that dead space allows for no respiratory gas exchange to occur. But in reality, there's going to be some gases that are exchanging just by diffusion. Okay? What I want you to see here, of course, these are all just vocabulary words, but the expiratory reserve volume is what you would inhale normally and exhale forcefully. Residual volume minus, or the air remaining after expiratory reserve volume has been exhaled. But here, total lung capacity is the vital capacity plus that residual volume I mentioned just in passing there at the end. So this is a pretty good place to stop before we start thinking about how things and why things are moving into the body and out of the body. And I'm just going to tease you here by showing you this slide where, look, all of a sudden we have to start thinking about not only oxygen. Notice we're not talking about gases anymore or air. We're talking about the components of it. What is the role of oxygen and what is the role of carbon dioxide?